Welcome back, AP Stats students. So we are moving on to part 3, and this is where we start seeing how our model deviates from the actual data. So I want you to think back. We started this whole conversation with talking about residuals and how far away from our line of best fit our actual data is. So with a linear model, it assumes the relationship between the two variables is a perfectly straight line. So the residuals are the part of the data that has not been accounted for yet. So the residuals are going, okay, how far off is this particular point? So a way of actually thinking about this is your data is your model plus your residuals. Let's use a pen. So it could be seen as y hat plus the residual gives us your data. Well, if you think about it in a roundabout way, that is actually how we calculated our residual. We took our actual data value and we subtracted it from our prediction, and we got our residual or a model. So what are our residuals actually accounting for? Well, to put it in a roundabout way, if everything is included, then either that the association between high school GPA and university GPA is in our model, or there's something else going on. And that something else is the residual, is the error that we haven't accounted for in our own model. So when the residuals actually speak. So residuals are a good indication of how well the model does. So does the model have value? So does the model make sense even? When you're using a regression model, and when a regression model is of value, there should be nothing interesting about the residuals. You should see no pattern whatsoever. If the model is good, the residuals don't show anything. So in our GPA model, we know that the points above are positive residual and the points below, or negative residual, are about even or equal on either side, both positive and negative. And the sum of those values suggests the residual should be 0, the sum of the residuals. Additionally, we hope that most points are near our least square regression line, so the residuals are small. Large residuals should be infrequent, suggesting a unimodal and symmetric distribution. If I say unimodal and symmetric, you should be thinking normal. So after we fit a regression model, we usually plot the residuals in hope of finding nothing. And that's the main idea. When we're looking at the residual model, we don't want to see anything. Nothing to see here. So how do we get an actual residual plot? Well, a residual plot is a scatter plot of the residuals, of the error measurements. The residual plot is the final test of how well our model represents the data. What we are expecting to see is no pattern to the residual scatter plot. So if you do find a pattern in the residuals, there may be a problem. And that's kind of the underlying thing. What else is going on here? So on the right, we see both our line of best fit, our scatter plot, and then below it is our residual plot. A pattern in the residual suggests a systematic relationship between the variables that has not been accounted for by our model. So there's something else going on. I think the way your book presents it is, does the plot thicken? That's what chapter 9 is about. A histogram of the residuals should appear mostly unimodal and symmetric. So again, sticking with our university GPA and high school GPA, if we're plotting the residuals, look at the axes. That's why we label these things. You see resid. The histogram of our GPA residuals appears sufficiently unimodal and symmetric. The model appears to meet all of our requirements. So remember our requirements again: quantitative, approximately linear, and then here it's also saying our residuals are approximately normal. Do note, we can also, instead of looking at a histogram, we could use a normal probability plot, or NPP, to see if that's approximately linear. That's another way for us to tell if our data is normal. So again, remember, normal probability plot. It's a helpful way of finding this stuff out. So if we go back to our model with body weight and backpack weight, we previously calculated the model. We have backpack hat is equal to 16.3, which is our y-intercept, plus 0.09 times the body weight. We've typed this in. So switching over to our graphing calculator, previously we had entered in our body weight and our backpack weight. We got our line of best fit. If we wanted to see, control doc, our spreadsheet or our scatter plot, we would have body weight as our x and our pack weight as our y. If we wanted, again, to get our line of best fit, we would go analyze, regression, and then let's do a plus bx for linear regression. We get the exact same equation. I want to look at the residual plot. And what I really like about the TI Inspire is if you just hit menu and then you go down to analyze. Now note, we went to 6 for regression, but right underneath regression, it says residual plot. Now the two things that it can show you, it shows residual squares. We had looked at that before. That would be the sum of the square errors. And if I went show residual plot, now it splits this in two ways, and I can see my scatter plot along with my residuals. Again, switching back to the notes, we see that we have our residuals, all of our errors lined up. Again, if I put the crosshair, that's where our two averages are if we're going to z-scores. The goal is nothing unusual. If we don't see anything strange, which we don't see a clear pattern here, there's scatter, then our model is a pretty good fit. So if you are using a TI-84, I outline specifically how you can get your residual plots. If you're using the TI Inspire, it adds a lot of benefits. So again, if I did my analysis, I'm going to make a control document, and I make a data and statistic plot. Because I did my analysis on my spreadsheet, I can also pull up the residual plot, and I can do this analysis. Now, it's a scatter plot, so what I want is a histogram, and what I'm looking for in my residuals is it's approximately unimodal and symmetric. Well, it's hard to tell from this histogram, which is why we offer another approach with the normal probability plot. Now notice the normal probability plot, we're looking for our data to fit a line. And we're also given our mean, which should be 0 if we're dealing with z-scores, and standard deviation. But this is not our standard deviation of our x variable, and this is not standard deviation of our y variable. This is the standard deviation of our residuals, of our error. So switching back again to the notes, if we're thinking about the residual standard deviation, the standard deviation of residuals, S sub e, measures the variability of the residuals, or how the points vary above and below our model. How far off is our predictions? So for the GPA data, S sub e, or the standard deviation of our residuals, or standard error, as some people say, is 0.2801, which means our data has a typical deviation of 0.28 from the predicted value. So we're above or below one standard deviation. Remember, standard deviation is a unit of measure above our line or below our line. Note, we always got to check to make sure that the residual plot has a consistent amount of scatter throughout the distribution. We check the equal variance assumption with what your book calls does the plot thicken condition. That's what chapter 9 is. Note, if we're looking at the plot of the residuals, there's a lot more scatter on the lower GPAs. There's more variability. And then the higher the GPA goes, the more concentrated, the less variability there is in our grades, which means from our model, it's less good predicting lower GPAs because chances are we don't have a lot of students at university from high school that had lower GPAs. But the higher the GPA, the closer our model fits. So the standard error of the residual gives us some power in what we're looking at. Oh, our data does display changes in the variability of the residuals. It appears the model is not as accurate at lower high school GPA levels, so we note that in our conclusion. Remember, we're reporting out what we see and then moving on. We're not trying to make any justifications. So you might be asking, where does this come from? Where can we estimate the standard deviation of the residuals? And that's just like asking, can you find standard deviation? And of course, we take the residuals. Remember, E is just our residual. We square those, we sum those, and then we're dividing by n minus 2. This should look familiar to the formula for standard deviation. If we unpack that idea a little bit, residual, again, is just our value minus our predicted value. We square it, then we sum it up, then we divide by n minus 2. And since those are all squared terms, we take the square root. This should look familiar. This is a modification resulting from two variables being involved as opposed to one. So instead of n minus 1 when there's one thing, now it's n minus 2. Do you have to do this by hand? Absolutely not. We will let the calculator do that for us if we need to do these types of calculations. So going back to our backpack problem, we do not need to subtract the mean if we're using our residual plot. If we pull up our backpack information, again, if we wanted to switch back to a histogram, we just switch to our histogram here. Either way we're looking at it, whether we're in our notes or on our calculator, we see that it's roughly unimodal. There is one peak. And if we're looking at the residuals, we're looking at z-scores. So our average error should be 0. So E bar is our average residual. It should be 0. If we make a histogram or a normal probability plot of the residuals of the backpack data, it should look unimodal and roughly symmetric. And does it? If it does, then we can apply our 68, 95, 99.7 rule to see how well the regression model describes the data. How well is how many standard deviations of our residual does our data fall in? So the question is, do 95% of residuals fall within 2 standard deviations of 0? Well, if we're looking at the histogram, all of our data is within 2 standard deviations because our standard error, if we look at our table, which is this line right here. Also note, this is our mean, this is our n, this is our error, standard error, and then count missing. So we have all of them. What we're looking at is at 2.1. If I went 2.1 to the right and 2.1 to the left, that would be 1 standard deviation, give or take. If I went another 2.1, all of my data is within 2 standard deviations of my mean, or of 0. So if we go back to our notes, 100% of our residuals fall within 2 standard deviations of 0 from our residuals. That means all of the data is accounted for, and there's not something else going on. Which leads us to the last bit, and then we will end these notes, of the coefficient of determinations, or what is this R squared term that I keep referencing? And it comes from the standard errors, the standard deviations of our residuals. So the coefficient of determination, or R squared, is the portion of the variation in the values of y that is accounted for by our model, or the least square regression model. And we can calculate R squared using this formula. Again, we use our calculator for this. But you could. It's 1 minus the sum of the square errors, or this is E squared, summed up, divided by the sum of the square totals. So what do we mean? Well, we said this was E, right? Y minus Y bar squared. Well, the sum of the square totals is taking each Y value, or output, from our mean, or our Y bar in this case. Square, add those up. R squared is 1 minus the proportion of variation not accounted for by the model out of the total variation and the response variable. Thus, the variation that is accounted for, like 1 minus, this is the variation from 1 that's accounted for in our model. Both of them should add up to 100%, or what's going on. The variation in the residuals is one big factor in assessing how well the model fits. In our GPA data, the variation in the residuals was 0.2801, or 0.280091, we round up. The variation in the response variable was 0.4472. That is comforting, suggesting the model has less variability than the original data. So where did I get this 0.4472? If we're just looking at our university GPA, that's our actual output. This is our one variable statistics, one of our statistics, just for university GPA. And if that's our output in this case, that's our standard deviation. So that's comforting, suggesting the model has less variability than the original data. Our model is more closely tied to the outputs. So this R-squared term, if the correlation were 1 and the model predicted the college GPAs perfectly, the residuals would all be 0 and have no variation. If it's a perfect model, then everything falls on that line. There is no scatter, there's no variation. But we found that the correlation was 0.7795, which is not quite perfection, but that's a moderately strong to very strong relationship. So we did see that the model residuals has less variation than the college GPA. We can determine how much the variation is counted for by the model and how much is left in the residuals. So how much is in our model, how much is outside our model. Because remember, data is equal to the model plus the residual, or y hat plus e is equal to y. The squared correlation, R squared, gives the fraction of the data's variance accounted for by the model. So thus, 1 minus R squared is the fraction of the original variance left in the residuals. 1 minus R squared is the coefficient of non-determination. How much is not accounted for in our model? R squared, therefore, is how much variation is in our model. So we say this. Literally, if we take our R and square it, so R was 0.7915 in case of our GPA data, we square that, we get 0.6076. Thus, 61% of the variability in college GPA is accounted for by variability in high school GPA. And 39%, which is 1 minus 61% of the variability in college GPA, has been left in the residuals. It's not accounted for by our model. Therefore, all regression analysis include this statistic, although by tradition it is written R squared. And R squared of 0 means that none of the variance in the data is in the model, which also means all of the variance is still in the residuals. Our model doesn't account for any of the variation. When interpreting a regression model, you must always correctly interpret R squared. So let me give you the sentence again. And let me repeat that. Anytime you are working with a correlation and regression model, you must always interpret R squared. So now we're adding on. What do you mean, or how should you write out when you're discussing R squared? We're not getting cute, we're not getting creative. You're going to say R squared, so blank percent of the variation in the response variable, whatever it is accounted for by the variation in the explanatory variable, or the model. As I indicated before, do not get creative or clever. Just use this sentence structure or not risk getting credit. The AP is not asking you to be creative. They're just looking that you understand what you're doing. So we're going to repeat this every single time. So how big should R squared be? Well, R squared is always between 0% and 100%. What makes a good R squared depends on the kind of data you're analyzing and on what you intend to do with it. The standard deviation of the residuals is a good indicator of the validity of the regression model by telling us how much our actual data deviates from the predicted data. When reporting a regression model, you must report Pearson's R, R slope, R intercept, and R squared. This will give the audience a complete picture of the value of the model. So we are doing SODS plus R plus R slope and interpret, our y-intercept and interpret, and R squared and interpret that. In interpreting and analyzing a regression model, you now have several items that must be included. So with a scatter plot of data, our description of our distribution, R and R squared, our interpretation of R squared, the model itself, a description of the model, which means interpretation of the slope and intercept, scatter plot of the residuals, a histogram of residuals, or a normal probability plot. This is a lot, which is why we take it step by step, and we're going to just focus on this one bit of linear analysis. So we're going to end it here. Our last video will give you things like an overall wrap up and go through a full example problem that you should be able to do. I will see you in the last part of Chapter 8, Falcons, in the next one.